As Dom said, I'm in the Center for Reaction Engineering at AbbVie, and that's one of our centers of excellence. And it's very interesting to be here to talk about this particular project today, because I think you'll see a lot of cross-functionality work between our center and one of our newer centers, the Center for PAT. So today what I'll be talking to you about is how we took advantage of both automated lab reactors and online FTIR to build what we feel is a robust kinetic model that helped us really fundamentally understand the process for an API project in its late stage. So to do that, I'll give you a brief outline of what I'll talk about today. First, I'll establish the problem statement as we received it from the API team, and then what I'll do is I'll walk you through how we approached the problem and how we plan to solve it using online IR spectroscopy. We did this by building a chemometric model using IR, and that allowed us to put together a kinetic model with DynoChem, and then I'll just summarize by describing some of the overall benefits and learnings that we obtained from this particular project and what it really meant for us as far as process development is concerned within process R&D. So in particular for this project, this is actually one of the reaction steps as part of an API project. What happens here is the team takes CDI, puts it into a solution of THF, so it resides actually as a slurry, and then they dose in over time 1.1 equivalents of trifluoroethylamine, or TFEA. And the objective is to make this activated complex that I've highlighted here in red, and this is to be used in further applications for the API. This also liberates a molecule of imidazole as a byproduct, and unfortunately this activated complex is itself subject to overreaction in the presence of TFEA. And in the engineering world, this is really sort of a classic series consecutive competitive reaction. So we're familiar with this type of reaction, but not having studied its exact kinetics, we don't really quite understand, or at least at this point in time, when we got on board the API team, what these relative rates were. And the team was interested in understanding a number of different fundamental problems. One thing I should mention is that this particular chemistry, as it had been run previously at manufacturing sites in our own pilot plant on site in North Chicago, this is actually a very robust chemistry. It's worked successfully well, and the team hasn't really noticed any particular problems with it. But still, as far as late-stage development is concerned, the more understanding we have about a project, the more weight it carries when we justify our process controls when we go to file this procedure with regulatory agencies. So the team in particular was interested in what would happen if we took all of the TFEA and added it in at once. That would indicate a very severe failure mode where, because the addition of the TFEA is exothermic, that can induce local hotspots. What do temperature variations do to the ratio of these two rates? And in particular, there could be mixing limitations associated with this type of chemistry. These classic overreactions can be very problematic, in particular where if there's an area of high activated complex concentration in the presence of TFEA, that will form the urea byproduct that we don't want and have to reject, in addition to extra imidazole. Worse yet, we'll also be consuming the activated complex we need for further development. And one final point to make is that the CDI is actually a mutagenic impurity. And so the team is most concerned with assuming that as long as we can consume all of the CDI and verify it within our process constraints, then we can consider our process fully robust. So to do this, we reasoned that a complete kinetic model describing these two reactions and understanding the fate of the activated complex would give the team a multitude of reaction conditions and give them power to probe those very quickly using DOE. Now, at this point, there actually had been an HPLC method in process. The analytical team had done a very good job of putting together, for what was actually a very complicated system because the materials can degrade in the presence of water for HPLC, a derivatization method so we could track the concentrations of CDI and activated complex at any given time. The problem with that is it requires a derivatization, and it takes at least 30 minutes to prepare each of those samples. So if we desire high data-rich quality experiments that we can turn around quickly, this type of method wasn't really amenable to what we were looking for. And that's when we actually turned to the online IR probe. That would give us in situ reaction analysis. It would make sampling significantly easier, and the frequency with which we could sample could be significantly increased. But there's a lot of risk associated with that. By the time we got involved in this project, we had about 3 months to come up with a full kinetic model and understand this. So any time we spent in the lab where we tried to develop this model and we failed, we're already significantly behind the 8 ball then from that point. So we knew going into this that we would take on some level of risk for this particular system. There hadn't been any previous models developed. Some exploration had been done, but nothing substantial. But given the potential advantages of using the online R and I guess the attractiveness of being able to do this to build the chemometric model for the kinetic analysis, we decided to go ahead with the online IR analysis. This was actually the very, very first experiment that we did. All we did was we took CDI and THF and added one equivalent of it at a time of TFEA. And then figuring if we see any significant changes in the IR spectra that I'm showing you here, that would give us some level of confidence that this would be a useful technique for us to probe further. If we had seen nothing, we might have abandoned it completely, and then it's an afternoon's worth of time in the lab and nothing else. But you see here, looking at the wave numbers here, I've pointed this is the initial curve for the CDI in the water plot. So you see it has this larger peak around 1750 and then a smaller shoulder around 1730. And then after adding in one equivalent of the TFEA, we do see this peak disappear, and we see this peak form. We attribute then at that time to the activated complex, and then continuing to add another equivalent of TFEA, that's when we begin to what we at the time we also thought was the urea. And so seeing this very simple experiment gave us confidence that we'd be able to move forward with IR as a serviceable probe for this particular reaction. And it was at this time that, again, we had CDI and TFEA available to us. We had an isolated sample of the urea, but we actually didn't have maybe the most interesting component of them all, the activated complex. We don't really have, at this point in time, a simple workup method where we can isolate this particular molecule. It is commercially available in smaller quantities, but at the time we didn't have this available to us. So what we did at this point was we took pure samples of each of these three components and simply ran them against the IR to see if there's any significant differences in these spectra. And I think you can see it's pretty clear that we do see a number of different peaks in different locations for all three of those components. You can see the carbonyl peaks out for the CDI and the urea, and you can see the trifluoromethyl peaks native to the TFEA and the urea substrate as well. So again, this is just building the case one step at a time to be certain that not only were we just going to run to the lab and throw materials into the reactor and hope that the IR would tell us what we would expect to see, doing it this way allowed us to gradually build on the knowledge that we were trying to acquire one step at a time. So from this point, what we did was we refined the data now by taking known solutions of each of these components, and at this point, we had actually obtained the activated complex as well. So these are the three components of interest, the CDI in green, the activated complex in blue, and the urea in red. And you can do this with either raw absorbance or the first derivative or the second derivative of the data. Sort of our house rule that we usually default right to the second derivative. And the reason that we like that is because it helps sharpen some of the peaks. I think this is a pretty good example of that. And it helps correct for the baseline shift and the drift that you might see in the spectra. So before you run into any issues where you may have picked the wrong peak in the raw absorbance, we tend to like to look at the second derivative at the outset. And what we're looking for here are peaks that are clear of interference from any of the other species. What we'd like to do is build a univariate model, which only that means one wave number for one component. So if we can do that, that makes our lives analytically significantly easier. And you can see that the CDI gives a nice sharp peak around 867 wave numbers. There's no interference from either the activated complex or the urea. So we went ahead with that as our reference point for the CDI. And we did a similar analysis for the activated complex. This peak here in blue is at about 954 wave numbers, and you can see that's clear of this peak in the urea, and there is no peak for the CDI in this range. So this gave us two good starting points for these particular components. And all these couple of plots that I'll show you here, these are just simple calibrations taking the wave number or the intensity at that particular wave number as a function of the known concentration. All these are our stock solutions. Again, this is another afternoon's worth of experiments. It's very simple to build these calibration models. And you see that we get a linear fit for the concentration of CDI using that peak. And we did the same thing for the activated complex at 954. And so now that we have these two univariate models for these two compounds, we should be able to put together some sort of kinetic experiment that will help validate this before we move deeper into some of these details. But we were actually very surprised, as we ran a very simple experiment where we took a solution of CDI, this is a purely homogeneous solution in THF, into which we dosed TFEA over time. The purple curve represents the concentration of CDI, and you can see that that pretty much goes to zero, which is what we would expect. But these two curves relating to the activated complex. And this is where, at least how we proceed with these sorts of things when we do analysis, is thinking about the overall mass balances. This curve in green is the original curve that I had mentioned that we used for the activated complex at 954 wave numbers. And it turns out that we were off by about 25% in terms of closing the overall mass balance. So we knew there was something wrong with that particular wave number. We weren't sure what it was. we decided to look deeper into some of those details in the second derivative. And it turns out we found another wave number in the second derivative for the activated complex at about 1,370 inverse centimeters. And sure enough, that's the dark blue curve you see here. And it turns out that actually helped us close the mass balance. So before we had gone and run 12, 15 experiments and then realized we had miscalculated, we did a simple experiment to verify that the model had worked. And that actually turned out to save us quite a bit of frustration and time later on. So with this, at this point, now we have a revised model using the activated complex here now at 1370. Again, you see the linear fit as a function of the activated complex concentration. And so now we're able to go ahead and really build the kinetic model. So we did this using the automated lab reactors and the online IR probe. We did this at two different scales. I'm showing you the 1 liter scale in which we investigated the slurry effects. This is the slurry of CDI and THF. That's the milky white mixture you see here. And then when you add in the TFEA after dosing, it clears up the solution quite nicely and it turns that golden color. And in particular, we just used syringe pumps for dosing and then connected the IR probe in place. For all of the homogeneous kinetic studies that we did, and that's what I'll be talking about from this point forward, we did these in reactors of about 100 milliliters of size and about 50 mils of liquid volume. So I won't go through all of the kinetic experiments that we ran, but what I want to do is I want to show you some of the key observations that we made, because this really helped piece together the model that we were dealing with. Now at the outset, the API team said, these are the two reactions you'll have to consider. And so this is what we had built all of our understanding up to this point. But we encountered some issues. In particular, we had run a number of fed batch experiments where we saw this induction period. And we didn't really know exactly what it meant at the outset, and we considered a number of alternatives. And funnily enough, it's that autocatalytic effect, and we were talking about that a bit earlier today, that this type of curvature where you see this sigmoidal effect, you see that here in blue. Blue corresponds to the millimoles of CDI, and the red squares correspond to the millimoles of activated TFEA, or the activated complex. The purple curve I've drawn here is just to show you the total amount of TFEA that was dosed in over an hour. And in this case, you can see that sigmoidal character is intrinsic to both the CDI curve and the activated complex curve. And we talked about the possibility of being the dosing limited kinetics, or the possibility that a tetrahedral intermediate forms that is slow to convert to the activated complex. But we really kept focusing on this autocatalytic effect. And we suddenly suspected that the imidazole might really be the culprit there. It could act as an acid, it could act as a base. And since we're forming it, that would seem to make sense. There's none present at the outset of the reaction. That might be the key to unlocking all of this. So we did the experiment that was described earlier this morning. If we think something is autocatalytic, add the agent that you suspect is the catalyst to the outset of the reaction and see if that changes the rates. And that's exactly what we did, and sure enough, that's what happened. The blue curve is what we see in the control experiment when there's no imidazole present in the start of the reaction. And in this case, this is all batch, by the way, so this also removes any effects that if we thought there might have been dosing limitations with the reaction, this should obviate that. And then the red curve here indicates the total number of millimoles of CDI as a function of time. This is when I spiked in half an equivalent of imidazole at the outset of the reaction. And you can very clearly see that without imidazole at the present, the autocatalytic effect is very clear. When there's some imidazole present, the concentration drops immediately once the TFEA is added. The catalyst is already present. That is all consistent, and that makes sense. Funnily enough, this actually explains, and you'll see in a bit, why this process has been so robust. So noticing that we saw this curvature, we can rule out safely now the induction effect in the reaction intermediate. And we also noticed that, again, seeing this significant increase in the rate of CDI consumption by having the imidazole present tells us a lot really about what the appropriate mechanism then should be. And a point that I want to make in particular is, I mentioned at the outset about using the established HPLC method versus the IR method. The HPLC method was a consistent method, it would work, but there's no way we'd be able to collect this many data points. This is sampling every 30 seconds over 3 to 4 hours. And so being able to do this and acquire this level of fidelity of data and capture that shape of that curve over time isn't something that would be easily done by HPLC. Imagine having to take a data point and do a half-an-hour derivatization for every single one of those samples. You might even mask that or totally ignore it or chalk it up to experimental error. So this really helped us determine that the imidazole was playing this role as an autocatalyst. So now we actually have a revised kinetic model. So now we have three reactions to consider. The first reaction that I'll call by K1 is the activation of CDI by TFEA to give the activated complex in the first appearance of the imidazole. The second reaction that I'll call by K2 is the autocatalyzed version of K1. This is again just CDI activating to form the activated complex. And then of course we still have to consider the overreaction of the activated complex by TFEA, and this will denote by K3. So now we have three known reactions. We feel very comfortable about this, but we had lost a lot of time getting up to this point. So now we have to make do with minimizing the number of experiments that we need to run, but still understand this and put together a robust kinetic model. So how do we do that? Well, we reasoned that if we start from reaction 2 and we spike in a known amount of imidazole, that will give us a reasonably good estimate for K2 and activation energy 2. So we can run at different temperatures, and this is where DynoChem really helps us as a kinetic tool. We can extract reasonably good values for K2 and activation energy 2 from two experiments, just changing the temperature and changing some of the reaction conditions. This is now how we see our fits. So again, in these plots that you'll see, CDI is represented by blue open circles. The activated complex is represented by open red squares, and then the fits in each case are the solid curves. And these are all batch experiments, by the way. And we were closing the mass balance, and so we were confident that we had elucidated what was eluding us originally. Having now an estimate for the rate constant and second activation energy, we can now fix those values. We can go back to DynoChem, run two different experiments where we start from CDI without imidazole present in the reactor, and tell DynoChem K2 and activation energy 2 are fixed. Tell us what activation energy 1 and rate constant 1 have to be. This way there's no artifact that we're building into the second rate constants. We're just trying to, as best we can, estimate those values. We ran two additional experiments and came up with estimates for K1 and activation energy 1. And now we can go to activation energy 3 and rate constant 3, start from activated complex, add in TFEA, and then track decomposition of activated complex to estimate K3 and activation energy 3. We can do that in a grand total of 6 experiments to come up with 6 kinetic parameters, and that's what we did. Now, we want to verify that even though we put all of this together, that the model will still predict what we would see in different reactions. So we put this to the test at 2 different sets of reaction conditions, 2 different temperatures, different concentrations of CDI, different equivalents of TFEA, and in each case we started without imidazole so that we would induce some behavior for the first reaction without the autocatalytic effect, and then let that proceed naturally. And these are the fits that you see. And initially, I'll show you some of the fits that we were getting earlier. Our fits weren't anywhere close to this because we had been completely neglecting the autocatalytic effect of the imidazole. What you'll notice is that the activation energies and the rate constants for the first reaction, the uncatalyzed CDI activation, and the uncatalyzed consumption of the activated complex are all in the same order of magnitude. And the chemists in the room will feel that that should make some sense. It's the same TFEA molecule reacting in each case, and the carbonyl center is reasonably chemically similar in each case. So it's not too surprising that these are on the same order of magnitude. What really surprised us at this point was seeing a 2 order of magnitude increase in the rate constant for the catalyzed reaction, and a decrease rather by about more than 50% in the activation energy. And that really belies the robustness of this process. We had observed the byproduct facilitating the reaction of interest and having a minimal impact on the reaction we absolutely didn't want to occur under any circumstances. That is not how we intended to design the system, by the way. That's just by serendipity. That's how it worked out. We'd like to say that we did, but we're certain that we didn't. But nonetheless, you can see that now after accounting for that autocatalytic effect, we get these very excellent fits. You see the nice tight curves nearing the data points. And again, you see the benefit of being able to collect data points every 15 seconds or 30 seconds or so. You can just acquire so much more data, and you can truly capture the curvature in these types of plots. So now that we put the kinetic model together, we were interested in a number of other things. Some of this was actually what we discussed in the PCJ report, just to help elucidate some of the key features of the system in particular. So at 50% conversion of the CDI, for example, you'll notice that the rate constants or rather the units for the rate constants for K2 and K1 and K3 are going to be different because it's a binary versus a termolecular reaction for K2. So we did absolute molar rate comparisons just to make it a bit simpler mathematically. So at 50% conversion of the CDI that I've marked by this purple dashed line, we see that we get approximately equal concentrations of CDI and activated complex. And so this is when we should see a faster rate for the activated complex relative to the CDI in terms of how significant is that side reaction going to be. It turns out the catalyzed rate of reaction of CDI is still 67 times faster on an absolute scale than it is for the decomposition of the activated complex by comparison. This is the type of fit that we were seeing earlier. This is the exact same data set where we incorporate K1, K2, and K3. This is the type of thing that was stymieing us from the outset. We put this into DynoChem and saw this. And you can very clearly see that not accounting for that autocatalytic effect really gives a rather stark contrast between a good fit and a bad fit. Now, from a fundamental catalysis standpoint, we were curious. We figured we already have the tool set up. Why not put this to the test? I mentioned earlier that the imidazole could act as an acid. It could act as a nucleophilic base. But we were interested, is it more of an acidic or basic effect in the reaction? So we took N-methylimidazole, which no longer has that Bronson acid functionality, and ran the exact same control experiment. And it turns out it too acts as a catalyst in this reaction. That's the green curve to match the green for the N-methylimidazole here. And this gave us the indication that the imidazole itself in the actual reaction is probably relying more on the basic nitrogen functionality, perhaps as some sort of hydrogen bond acceptor. There is some literature precedent for that in base catalysis for these types of carbonyl systems. And for those of you interested in, well, just how minimal is that impact of the autocatalysis on the activated complex decomposition, we went back to DynoChem. And this is very simple once you have all this in place. This took just a matter of seconds to put this together. We added in a fourth reaction, which is the same as the second reaction for CDI. Now we assume that there's some degree of autocatalysis for the activated complex. We represent that by K4. And it turns out that DynoChem says that's of minimal impact. It's 3 orders of magnitude difference in the rate constant compared to the activation uncatalyzed for either activated complex or CDI, and almost 5 orders of magnitude difference in the rate constant for the catalyzed CDI reaction versus the catalyzed activated complex decomposition. So it's likely that this actually plays some sort of role physically, but it doesn't really have a strong impact on the overall process. To give you an idea, this is what we had anticipated seeing at the outset. We saw 2 reactions. You'd expect it to be bimolecular for CDI and TFEA. So you'd expect as soon as you add in the TFEA, that curve begins to drop monotonically and immediately. But we saw that induction effect. And with DynoChem, it's very easy to do these simulations, and this is that predictive power that I was getting at earlier. Now we have the ability to go back to DynoChem, simulate the situations and the conditions, and we can learn more about the process that we built from our IR kinetics. And this is just an example of taking the experimental data that we acquired and saying what the simulation would be if there were no autocatalytic effect. So this is what would happen if K2 were completely equal to 0. This is the simulation, and again, this is the experimental data. And you can just see that stark difference between those 2 curves. Just to summarize, we put together a thorough kinetic understanding of this system. We were able to do that by the use of the automated lab reactors, but in particular, the chemometrics that we were able to ascertain with the IR, in particular that they were univariate models. That saved us quite a bit of time in the lab. We were able to track by 1 wave number for activated complex and 1 wave number for the CDI. And that gave us quite a bit of utility in the lab and saved us from having to build a more complex univariate model. And the IR gave us the benefit of having these data-rich experiments. And you saw, I think, the benefits that we got with that associated with DynoChem and building that complete kinetic model. And in particular, this helped us really elucidate why this process was robust. Again, it's just very rare that you see that where the byproduct actually helps you and can be easily rejected. That is not something that we normally plan for, but we'll take it when it happens to us. And in particular, what this really all amounts to is this was a late-stage project. And this becomes something that of predictive power with kinetics. That's very persuasive information for process controls justification. Fundamental first principles information like that is often hard to come by, but when you can get it, it's virtually unassailable. And in particular, one thing I haven't shared yet is we can now do this at scale. And so we did this experiment in our own pilot plant. And I'm supposed to say this as a disclaimer. We did not recalibrate the probe in the pilot plant from what we had in the lab. So we took the exact same models that we had built in the lab, just for fun. This was just to see if this would actually work. And sure enough, the red curve is the CDI concentration. This is concentration as a function of time. This is as the point at which we started to add the TFEA. You can see the CDI concentration drops completely to 0 and remains stable over the rest of the reaction. The green curve is the activated complex concentration. You can see that begin to rise as the TFEA is added. It reaches a maximum, and because we always add in 1/10 of an extra equivalent, we do consume some of the activated complex, and again, that remains stable over time. So there's also that benefit as well. Not only do we get the kinetic and the predictive power, but now we have something that we can use online at a manufacturing scale. With that, I'd like to thank my colleagues in the CRE. In particular, I'd like to thank Mike Rozema. He's the team lead for this particular project in process chemistry. Ann Krzyzewski was the process engineering lead for this team. And Steve Doherty, I'd be remiss for my METTLER friends if I didn't bring up Steve as being the new lead for the Center for PAT. He's been instrumental in helping us get acquainted with the instruments and giving us the freedom and the ability to use them. And so I thank him for all his hard work with respect to that. I also thank you for your attention. That's all I have for you today, and I will gladly answer any questions.